Okay, so as we move on, we're a little bit more familiar and comfortable with working with a probability generating function. Well, we're going to try and relate that to some of our standard distributions that we've encountered so far. We are going to try and derive some of the general probability functions for those distributions, and some of them actually become quite simple as we make our way through the derivation. So I recommend you pause regularly as I go step by step. There's no point in misunderstanding or not being able to tell what I'm doing from one step to the next. And I would definitely want you to practice these on a regular basis. Would you be able to reproduce these derivations? You may well be asked to do that in the exam. Well, I'm starting here with the probability distribution, the general probability distribution for the binomial distribution. And the definition of a probability generating function is that it's the sum of a probability multiplied by the corresponding dummy variable. So let's do that with the expressions we have for probabilities here. So for the first one, it will be q to the power of n, since we know that it's an edge case and the other terms equal to 1, multiplied by t0. For the second one, we have the probability expression multiplied by t to the 1, probability expression multiplied by t to the 2, etc., etc., until the last term, which is going to be p to the n multiplied by t to the n. So this looks very much like the binomial expansion, except we have an extra term. We have the t term there. So I'm just going to do some manipulation here, because I noticed that the p and the t always have the same power. So why not write them together? So anywhere that I see a p, I'm going to combine it with the t. So the first term actually has pt to the power of 0. In the second term, I'll write the p and the t in a bracket, and that's to the power of 1. And I'll do the same all the way along. And if you notice, I now have a binomial expansion, where the two terms are q and pt. So I'll go ahead and write that in the factorized form of a binomial expansion, q plus pt to the power of n. Q isn't used in the standard formulas or the standard results, so I'm actually going to swap out the q for 1 minus p. We're going to end up doing this regularly because we're not often asked to prove something in terms of q, but rather in terms of p. Q's easier to work with, and it's easier, we generate easier expressions, but the final result we always want to try and reconvert back to being in terms of p. In the next question, we're told that we're working with a Poisson distribution where lambda equals 1.1, and we're asked to show that its probability generating function matches the one that's given. So we'll start just by writing out the probability function for the Poisson when lambda equals 1.1. And we're going to go back again to the fact that a probability generating function is the sum of the probability multiplied by the dummy variable. So I'll start by substituting in our specific probability statement. So it's the sum of e to the negative 1.1 multiplied by 1.1 to the power of x all over x factorial multiplied by the dummy variable. Okay, I noticed that e to the negative 1.1 is a constant, so I'll take that outside, and I'm left with 1.1 to the power of x over x factorial multiplied by the dummy variable. So I'm in a situation again where I notice that the 1.1 and the t have the same power. So why not write them together in a bracket to that power? So from there, I get e to the negative 1.1 multiplied by the sum of 1.1t to the power of x all over x factorial. Okay, that's been simplified enough. Let's start substituting some x values and see what we can generate. So we substitute x equals 0, we get 1.1t. And then after that, we'll get 1.1t squared over 2 factorial, 1.1t cubed over 3 factorial, etc. And you might start to recognize that actually in my square brackets, we have the Maclaurin expansion. So specifically the Maclaurin expansion for e to the x, where in this case x is 1.1t. So that actually means that I can replace the whole of this square bracket with e to the power of 1.1t. Okay, so this is nice and simplified. Let's take a couple more steps. I'm going to combine those powers since we were multiplying, and then I'm going to factorize. And here is the form we were asked for in the question, and also the generalized probability generating function for any Poisson distribution with a given lambda. Okay, let's see how this might work with a geometric distribution. We've been told that a fair tetrahedral dice is rolled until the dice shows a 4. The discrete random variable represents the number of rolls up to and including the first instance of a 4. So right there, we should recognize a geometric distribution since we were looking for the first success, and the value of p for this geometric distribution is 1/4. So as before, let's start with a probability function. So in general, we know that the probability that x equals x is going to be failure to the power of x minus 1 multiplied by the 1 success. In this case, it's 3/4 to the power of x minus 1 multiplied by 1/4. Okay, once again, the probability generating function is the sum of the probabilities multiplied by the dummy variable. And we'll go ahead and substitute our probability statement into this expression. Okay, and from here, let's go ahead and substitute some values in. So starting with x equals 1, there is no x equals 0 in the geometric distribution. Starting with x equals 1, we'll generate a few terms of this sequence, of this series. And as we generate them, I recognize that there is a common factor. There's definitely a quarter in every single one of these, since that's the probability of success. And there's definitely a t value in all of these. So I'm going to factorize out 1/4 t. And that leaves me with 1 plus 3/4 of t plus 3/4 squared t squared plus 3/4 cubed t cubed, etc. So I hope you can start to recognize what might be happening here. I'm just going to take a second or another line just to combine the 3/4 and the t, since I recognize they always have the same power. So I'm just going to write them together in a bracket. So 3/4 t, 3/4 t squared, 3/4 t cubed, etc. So I hope you can see here, what we have is we have a geometric progression or geometric series where the first term is 1, the common ratio is 3/4 t, and since the geometric distribution is infinite, we're looking for the sum to infinity. So the sum to infinity, a over 1 minus r. So I'm just going to substitute that in and see where we can go from here. Well, let me expand these brackets. I'm going to multiply in by the 1/4 t. And from here, we're going to try and see if we can get the form we were asked for in the question. Well, the probability of success was 1/4, so I can swap that for p. And the probability of failure was 3/4, so I can swap that for q. But just like I've said before, we'll try and get everything in terms of p, so the q swaps out for 1 minus p. And as complicated as this looks, we got there through those sequential steps. Okay, so we'll do one more for the negative binomial. So starting in the same place, the probability function for the negative binomial is x minus 1 c r minus 1, as in an NCR statement. P to the power of r, q to the power of x minus r. The probability generating function is the sum of a probability multiplied by a dummy variable. Let's go ahead and substitute our generic probability function in and see where we can go from there. So a technique that I've been using up to now is to spot when the powers on terms match with each other, so I can kind of bracket them together. Well, I want to see if I have an opportunity to do that here, but T has a power of X, while P has a power of R, and Q has a power of X minus R. And at first glance, it might look like nothing matches, but actually I can rewrite T to the X as T to the R and T to the X minus R. Doing that, I form two pairs of terms that have matching powers. So I'm going to go ahead and try and make use of that. So once I've done that, I can bracket those off together. So I've got PT to the power of R and QT to the power of X minus R. PT to the power of R is not quite a constant, but it's independent of X. So I can take that out of the summation for now. And what I'm left with is the sum of X minus 1 R minus 1, QT to the power of X minus R. And earlier in the question, we were told that we could use a substitution. And the substitution here was that the sum that we have can be substituted for 1 minus QT to the power of negative R. So I'll make use of that right now. I've got an R and a negative R. I can rewrite it as a fraction. So I'll do the whole fraction to the power of R. And we're getting close to what we were asked for. As long as I swap out the Q for a 1 minus P, so get this expression in terms of P only, then I have the form that we were asked for. And those multiple steps have got us to the general probability generating function for a negative binomial distribution. Okay, so practice these derivations. Pause if you want to watch back through the video and look for the individual steps and do them yourself, but practice these on a regular basis, one a week, one every couple of days, and just make sure that you can flow logically through each of the steps that will get you to the derivation.